Well, welcome to section 2.1, quadratic functions. In quadratic functions, the chapter begins with the definition of polynomial function, and basically a polynomial function is going to involve some terms with some x's and integer variables on there. So we wouldn't have, for instance, this term would not be 3x to the square root of 4. N is going to be a positive integer counting on down. To be perfectly honest, actually a polynomial could just be a constant term. For instance, f of x equals 7. However, we very seldom talk about that being a polynomial, just the normal constant function. So in this section, the specific polynomial function we're going to be looking at are quadratics, which you certainly have some experience with in this course and prior to this course, but that is when our highest exponent is a 2. So we have ax to the second. In this case, we're 7x squared plus 3x plus 5 would be a quadratic function. And we have, with our background, we know that those graph to be parabolas. And the fact that we're just talking about quadratics brings up quadratic formula, for instance. I suspect that probably everyone in here or everyone that's viewing this may have some experience with quadratic formula. Hopefully you remember it. It would basically say that when we set a quadratic function equal to 0, we can find the solutions for x by saying x is the opposite of b plus or minus square root of b squared minus 4ac all over 2a. And while it's certainly worth memorizing this, I think it's kind of nice to see where that comes from. So I'm going to go ahead and take this quadratic function, just a general quadratic function, set it equal to 0, and I'm going to go through the process of solving this for x by completing the square. So as you may recall, for completing the square, I'm going to factor out the lead coefficient. I get a times x squared. When I factor an a out of here, I'm dividing out an a, so this becomes plus b on ax. Note, if I distribute this back in, I get ax squared plus the a's cancel, bx. I'm going to leave a blank, and I'm going to subtract that c on both sides, put a minus c on the opposite side. Okay, and then hopefully we recall, to complete the square when we're in this form, we take half of this term, so this is b on a times 1/2, and we square it, or we get b on 2a squared, or we get b squared on 4a squared. And that's the value I'm going to put right in here. So I'm going to go plus b squared on 4a squared. Now, I just changed the value of the left side of this equation. I just changed the value when I put this here. It wasn't a part of this equation. What I really did was, if I distribute this a, it cancels one of the a's in the bottom. I really just added b squared on 4a to the left side, so I balance that over here. Okay, that makes the left side a perfect square. That would be a times x plus b on 2a squared equals, I'm going to go ahead and get common denominators here, negative c times 4 times a on 4a plus b squared on 4a, or a times quantity x plus b on 2a squared equals, I'm going to write this as b squared minus 4 times a times c all on 4a. Okay, we continue solving. My goal is to get x alone. I'm going to divide both sides by a. I get x plus b on 2a squared equals b squared minus 4ac all on 4a squared. Next, I'm going to take the square root of both sides. So x plus b on 2a equals plus or minus b squared minus 4ac all on 2a, but this is a radical up top. Square root of the top over square root of the bottom. Of course, we need the plus or minus. And then I'm going to solve for a by subtracting, put a negative b on 2a plus or minus square root b squared minus 4ac all on 2a. And there's our quadratic formula. In some respects, I almost like it this way, and we'll come back and talk about that in just a moment. But since I have common denominators, opposite of b plus or minus square root of b squared minus 4ac all over 2a. So there's where it comes from. Again, it'd be a lot of work to have to go through that process all the time, and therefore one of the formulas, and if you know me well, in my philosophy of math, I'm definitely not a memorize type math person, but this is probably well worth memorizing. Okay, standard form of a quadratic function. This is our most useful form. If you took this course with me by now, we would have already probably looked at playing some parabolic charades, and you might understand why that's a beneficial method, a beneficial form for us to have it in, rather than to have this as some ax squared plus bx plus c. Rather than have it in this form, it's probably worth completing the square, particularly if we want to think in terms of the graph. So let's talk about that formula just for a moment. Let's assume for our purposes right now, we know a may not be 0. Let's assume a is positive. So x minus h, when I square it, it could be 0, but when I square a number that's not 0, it's always going to be positive. So if a is positive, I get a positive number times either 0 or a positive number that I'm adding on to some other number. Therefore, any value of x that's not equal to h, so I get a positive or a negative result inside of here, x minus h is positive or negative, is going to result in adding to k. So our y value is going to always get bigger than k unless x minus h is 0. Therefore, the graph is going to always get taller except when x is h, which makes h the x-coordinate of the vertex. And when x is h, I get 0 squared 0 plus k. K is the low point of our parabola. And of course the opposite applies if a is a value less than 0. So I'll often refer to this, the MyVox is h. Most interesting value of x. Most interesting value of x is h, because h is the thing that makes this value 0 right here. If this is 0, then y value is k. If x minus h is not 0, the y value is going to be more than k. If a is negative, it's going to be less than k. So stands to reason, vertex is at hk. All right, now, minimum and maximum values of a quadratic. Negative b over 2a, where have we seen that before? And all this means is the height at negative b over 2a. So this is just an ordered pair at the vertex. So let's go back and let's take a look at this for a moment. Now this is the spot where the value, where the function becomes 0. This is the value of x that makes the function 0. Let's say, for instance, we have a parabola quadratic that looks something like this. The x solutions to this equation or this equation would give us those 2 points. So negative b over 2a plus or minus something. So negative b over 2a, I go somewhere right or left. My x value takes me somewhere right or left. And then it says the zeros are to the right or left the same distance from there. So negative b over 2a, it stands to reason, must be halfway between the two zeros. And halfway between the two zeros is where the vertex must be. So right there, as I said earlier, sometimes I like thinking of it in this form. This negative b over 2a, or negative b over 2a, we've seen it before in quadratic formula. That's the center of the parabola, because from the center again, we go to the right a distance and the left the same distance, we get our zeros. So negative b on 2a must be halfway between those. Hope that makes some sense to you. And again, f of negative b on 2a is just the height at that x value. So just like to tie in some loose ends there. All right, let's take a look here. If I match the quadratic function with its graph, the graphs are labeled A, B, C, D, as we can see. MyVox is 2. Do any of these parabolas have a vertex at 2? Well, the vertex of this is over at 4, the vertex of this is at 0, the vertex of this is at 2, and the vertex of this is at 0. Now, you might also note that this parabola is going upwards. That's because this is a positive. So number 5 is C. Number 6, the MyVox is 0. I'm squaring here. To square 0, I needed 2. To square 0, I need 0. So this graph is not shifted to the right or left at all. It is shifted up 3, and it does open upside down. Up 3, upside down, no right or left shift, D. Shifted up 3, but not right or left, and it opens up. B. Upside down, but right 4. Right 4, upside down, A. That is a skill I hope you become absolutely excellent at. All right, once we become good at that, and we have a graph and we have a quadratic in standard form, we can graph these things instantly, including how fast they grow or how steep they are. Sketch the graph of the function and compare its graph with y equals x squared. Okay, well, I'm going to compare its graph with y equals x squared first. The MyVox is negative 3, so our vertex is negative 3. When x is negative 3, all of this becomes 0, and we subtract 1. The MyVoy, most interesting value of y, is negative 1. I might not even normally write that. So I'm left 3, down 1. That's our vertex. Now, where do we go from there? Standard parabolic growth. On regular old y equals x squared, if we were to graph that, we might go 0 gives us 0, 1 gives us 1, 2 gives us 4, 3 gives us 9, and then we might also notice this is the case. A regular old parabola from the vertex is going to go over 1 up 1. From the vertex is going to go over 2 up 4. From the vertex is going to go over 3 up 9. It's standard when the lead coefficient is 1. And our lead coefficient here is 1, but it's negative 1. So this is standard and upside down. So from the vertex, over 1, down 1. From the vertex, over 2, down 4. From the vertex, over 2, down 4. And if I had room, I'd go from the vertex, over 2, down 9. So our parabola looks something like this. How does it compare to y equals x squared? Well, it is left 3. I just go order of operations. Upside down. And down 1. Standard growth parabola. So if this was a 2, for instance, if I had y equals 2x squared, I would say it's twice as tall as standard. Standard's over 1 up 1. 2x squared would be over 1 up 2, over 2 up 8, over 3 up 18, etc. Okay, good stuff. Identifying the vertex of a quadratic function in exercise 17 through 20. Here we go. Describe the graph of the function and identify the vertex. To do that, I want to put this in standard form. I want this to look like a times x minus h squared plus k. So I want to complete the square on x. And sometimes not so easy. Sometimes it's a little trickier than the ones we've looked at in the past. So I'm going to isolate my x's. I've got just an x squared plus 3x. Leave a blank and keep my plus 1/4 here. So this is what f of x is. I haven't changed anything, just the form. Still the same function. So I need half of 3 squared to go right here. So this becomes x plus 3x plus 9/4, still plus a 1/4 here. Now this is f of x. This was not here. I just added 9/4 to this side, unbalancing the equation. So I could come over here and add 9/4 to f of x, but I'm going to instead just subtract 9/4 here. So I add 9/4, I subtract 9/4. This is most definitely still equal to that. And I get x plus 3/2 squared. And you can FOIL and check, probably worth doing that. Let's see, I'd get an x times 3/2, 3/2 x, a 3/2 times x, 3/2 x. That's 6/2 x, 3x. Got it. 1/4 minus 9/4 minus 8/4 or minus 2. So describe the graph of the function. Well, the graph of the function, I'm not going to write it down here, looks just like x squared, except it is to the left 3/2 and down 2. Vertex, we will go ahead and do that. Vertex is at my box, negative 3/2. When x is negative 3/2, this part becomes 0, and y becomes negative 2. Okay, that's a lot of what we're going to be doing here. Describe the graph of the quadratic, identify the vertex and the x-intercepts here. Got a little bit more to do here. Use graphing calculator to check. Okay, so I need to factor out a negative 4 out of the first two terms. That would give me x squared minus 6x. Leave a blank. Separate the minus 41 out. Half of negative 6. I'm completing the square here. Half of negative 6 is negative 3. Negative 3 squared is positive 9, but that did not exist. What did I just do to this side of the equation? I just really subtracted 36. So I'm going to balance it by adding 36 right back on. And I get negative 4 times x minus 3 squared minus 5. So describe the graph of the quadratic function. Here's my description. It looks just like y equals x squared, except it is to the right 3. My box is 3. It is 4 times as tall, but it is upside down, and it is down 5. Vertex, 3, negative 5. X-intercepts. Now, for the x-intercepts, I could go quadratic formula here. I could go back to here and go quadratic formula. But if I've got the square completed for the x-intercepts, I want to know when y equals 0. I'm going to go negative 4 x minus 3 squared minus 5 equals 0. That'll give me the x-intercepts, the x values that give me a y value of 0. So this becomes real quickly here, I get x minus 3 squared equals, I'm going to add 5, I'm going to divide negative 4, and now I'm going to take the plus or minus square root. So I get x minus 3 equals plus or minus square root of negative 5/4. But I can't take the square root of a negative unless I'm dealing with imaginary numbers. Therefore, there are no x-intercepts. Let's see if that makes sense real quickly. Quick little thumbnail sketch. The vertex of this would be right 3, down 5. And this is opening up downward. This is upside down. Oh, of course, there's no x-intercepts. Had this been plain old 5-force, I'd just add 3 to the other side, and I would get, oh, the x-intercepts are x equals 3 plus or minus square root of 5 on 2, or on square root of 4. Okay, jump the gun a little bit here. Here's number 30. Should have come down and handled that one first. Once again, we're back in this set where we're just supposed to describe the function, find the vertex, excuse me, complete the square. So I need to factor out a 2. Note, if I distribute that 2 back in, I get 2x squared minus 1x. Separate the plus 1. Haven't changed anything other than just the form. I need half of negative 1/2, or negative 1/4 squared. I need half of this term. Half of a half is a fourth squared. So I'm going to add in 1/16 here. But I just invented that. What did I really just change this side of the function by? 2/16 or 1/8. I really just added 1/8 that didn't exist before. So I subtract 1/8. And I end up with 2x, it would be minus square root of 1/16, 1/4. And I get 8/8 minus 1/8 plus 7/8. So our vertex is at 1/4, my box 1/4. When x is 1/4, all of this term becomes 0. The y value becomes 7/8. Describe the graph. Well, it looks just like x squared, except I'll go ahead and jot this one down, kind of abbreviate. It is right 1/4. It is 2 times as tall, and it is up 7/8. Okay. 3738, write an equation of a parabola in standard form. Okay, in standard form, I'm looking for this. F of x or y equals a times x minus h squared plus k. Well, h, I only need 3 things. I need to know a, I need to know h, I need to know k. And h, k are the vertex. So this is going to be a times x minus negative 2, x plus 2 squared, and k, negative 1 plus negative 1 or minus 1. I'm going to rewrite that because it's sloppy. So x plus 2 squared minus 1. Now, I suspect the book would teach you to do this way. They'd say, well, put 0, 3 in. Here's y equals. Put 3 in for y. We get a. Put 0 in for x. We get 0 plus 2 squared minus 1. And we get 3 equals, let's see, that would be 4a minus 1. We get 4 times a minus 1. We get 4a equals, add 1, 4, and we get a equals 1. Now, I'm going to tell you, if you got a problem like this, it's a little bit easier than that. Remember standard growth. To get from this point to this point, I go over 2, and how far up did we go? Up 1, 2, 3, 4. That is standard growth. That's an indication that a is 1. A normal old parabola would go over 1, up 1, over 2, up 4, over 2, up 4, standard growth. If this had been, let's say this had been 0, 7, clear up here, we went over 2, up 8. That's twice as much as what we would have expected. I would expect a to have been 2. But in this case, a is 1. We end up with the function f of x is 1 times x plus 2 squared minus 1. All right. Writing the equation of the parabola in standard form. In 39-44, write the standard form of the quadratic equation that has indicated vertex and whose graph passes through the given point. Well, standard form y equals a times x minus the x coordinate squared plus 1. This is I can put in a 4 here, sorry. X minus 4 squared plus 1. And it passes through 6, negative 7. Watch this, from 4 to 2. So again, here's what the book might have you do. They might have you now put negative 7 in for y, 6 in for x, solve for a, and then we know what a is. And you're more than welcome to do that. It doesn't take too long. But here's what I know. From my vertex to my point, I went over 2. From my vertex to my point, I went down 8. Therefore, from my vertex to the point that's on the graph, we'd have a look like that. So the graph is definitely upside down, y equals negative. A normal parabola goes over 2, up 4. This one went over 2, down 8, twice as far and upside down. I like that. Okay, let's see if we can handle that one here. Vertex, negative 1/4, 1. So I've got y equals a times x minus the x coordinate plus 1/4 squared minus 1. This graph, the vertex went over 1/4. And it went from negative 16/16 to negative 17/16. Negative 16/16 to negative 17/16. It went down 1/16. So my parabola is opening downward. What would standard parabolic growth do? Over 1/4 would normally go up 1/4 squared. It would normally go up 1/16. In this case, it went down 1/16, so it is standard. So this is either negative or negative 1, x plus 1/4 squared minus 1. Again, you could take this value for x, this value for y, plug them back in, and it really wouldn't be too bad. But I kind of like outthinking what's going on there. I kind of like doing it without plugging it in, showing my knowledge of how parabolas work. Okay, so there is your 2.1 assignment. You got a fair amount of practice there. Best wishes. This is definitely a section that we want to master, as are all, but this is very foundational. Even when you get into calculus, you'll spend an awful lot of time just working with quadratics and completing the square. So good luck. Come in with any questions that you might have.